Good afternoon, everyone. My name is Bob Hahn. I'm the president of Lumecon, and today I am joined with, as always, Michael Woznicki, our lead project engineer. Michael, say hello.
Good afternoon, everybody. Thanks for taking the time to join us today.
Today, we're very excited. Our subject matter is Optics 101, and we're pleased to have with us Joel Robinson today to present. Joel graduated from Michigan Tech University with an associate's degree in mechanical design. He began his lighting career at Lexalite International in the summer of 1994. And for those of you who don't know, Lexalite is a division of ALP, and Lexalite provides approximately 70% of all prismatic injection molded lensing to the lighting industry in the United States. They are located in Charlevoix, Michigan. And Joel has been designing and testing injection molded lenses and lighting components for over 25 years. Joel is also the author and co-author of 5 United States patents regarding lenses and reflector designs. Welcome, Joel.
Welcome, everybody. Hello. And today, as Bob mentioned, we're going to talk a little bit about optics. I believe Bob and Michael are both kind of monitoring a chat. If you have questions throughout this, I've asked them to go ahead and interrupt me with your questions whenever that seems like it's the right thing to do, rather than waiting to the end to give this a little more of a lively format. So as we move through here, feel free to put questions in the chat box, and either Bob or Michael will be taking an opportunity to stop me and ask those questions as they come up. With that, I think we will get started. We're going to talk today a little bit about luminaires and optical control, and in full disclosure, I stole a lot of the data that I'm presenting, or majority of the data I'm presenting today, from the IESNA ED150, which was an educational module the IES used to use. They've since updated that, so some of this data is a little bit old, but the optical control portion doesn't change, as it's mostly related to physics. What we're going to do today is talk about how we move light around. The most sources that we have what's considered to be a fairly Lambertian distribution, which means the light goes in all directions coming out of the source. That changed a little bit with LEDs, and the distribution became kind of hemispherical instead of spherical. But our goal in optical control is to take that distribution and move it around and change the shape of it so that we can get the majority of the light in the places that we need. And so we're going to talk about how we do that. We'll talk a little bit about reflection and refraction. We'll talk about how we use those things, and then how they apply to luminaires. And I've also got a few slides in here just to kind of show you some examples of those things. The first thing we need to talk about is light. When we talk about controlling light or doing ray tracing, historically that was always done in 2D as a single arrow. What really happens with lighting, though, I think, as everybody knows, is it's more of an array of light, a pencil or a cylinder, or oftentimes people view it as a cone. And the key part of the cone is that light diverges as it moves away. And so that's the challenge in optical control, is that intensity is always lessening as you move away from the source. So this is kind of the order we're going to go in, and we'll just move right on to the next slide, which the first one should be in reflection. And so the key part when we talk about reflectors is that there's really 3 types. There's what we call specular, some people call spread, semi-specular, and diffuse. And the difference between those is shown up in the best way here. Let's see, right here. Specular reflectance is kind of, you see the incident intensity over on the left hits, and the reflected intensity is essentially the same. It's the same angle from the incident surface, and it has the same intensity minus whatever the reflective surface is. So like if you were using a mirror 4 reflector that's 96% reflective, the intensity of the reflected ray would be 96% of the incident ray. What in reality happens, you know, you can think of a specular surface kind of as the sun reflecting off perfectly flat water. What in reality happens is there's always some waves, and you usually end up in this semi-specular range where there's an intensity ray that hits, but you get this kind of curve shape of intensity leaving the reflector. And so then you have to kind of instead of being simple and being able to deal with one ray, you have to deal with this spread of rays that come off that surface. And the reflectivity can still be the same. So you still could have the 96% reflective, but you don't have the luxury of it all going in exactly the same direction. And then on the far right, we have a diffuse reflectance. And that diffuse reflectance is kind of like snow. It's the exact opposite of that sun reflecting off the lake, which was on the left. We've got a perfectly diffuse surface. The light leaves in every direction with equal intensity. And so that is the most difficult to control. It is, however, the most visually pleasing. Snow, when it is in a full sunlight, can be very, very bright, but it is also very uniform, and we tend to like uniform surfaces to look at. I think I went by one slide here, so I'm going to back up real quick. The other thing we can do with these reflective surfaces is we can shape them, and we can do all kinds of things to control light with different shapes. Every shape has its pros and cons, and we can break those shapes up, and we can use facets of different shapes, or we can use segments of different shapes, or we can use a full parabolic shape, for instance, like the one you see there on the right. That's taking that light and attempting to put it all in a near parallel. A parabola is designed to be parallel. The reason that it isn't perfectly parallel is in order to be parallel, the source would have to be a perfect point. And all of our sources have some dimensions, and so it's impossible to get those things to be perfect unless we get a long ways away. And I have a slide at the end that will talk a little bit about that. So this is the only math I'm going to show today, I think. Don't hold me to that, but I think I only put this one in here. And this is basically Snell's Law. And it talks about how much the light bends when it leaves a material in refraction. And so we've moved from a reflective surface, which usually happens at the first surface. We have moved to a situation here now where in refraction, the light actually enters the material at the first surface, it bends, and then it bends again when it leaves. And if the two surfaces are parallel, the entry and exit surface, then the angle is the same. If we were to change the angle of the second surface or the first surface, then that ray that leaves would have a different angle. And that's how we move light with a lens, is we control the angles of those surfaces and the relative angles of those surfaces to be able to take advantage of Snell's Law. And we can then move the light around, or we can reshape that distribution that we talked about earlier. One of the, I think, first forms or lenses that was made in order to do some of this was old searchlights way back in history. They found out that they could take a big thick lens and make a parallel beam for navigation of ships. And not long after that, they found out that if they chopped that thick lens up into pieces, they could save material, make those lenses lighter. And the guy who did that's name was Fresnel. And so he made, they were able to make these Fresnel lenses, and that's essentially what we're doing whenever we do optical design, is we're taking a shape that we know we need to control the light, and then we're placing that on a surface in these different prismatic shapes to get the light to be controlled and moved where we need. So there's really three things when we do refraction that we have to worry about. We have to worry about light that might not get into the surface, the red light on the left-hand side. If the light hits at a glancing angle, then it isn't actually able to get into the material. And what you can kind of tell that if you think about a glass door. When they open the door, there's a place where if you're looking at the door, you're looking through it. But if you open the door, there's a place where it becomes a mirror. It becomes a reflective surface on the first surface. And that happens usually in plastic materials somewhere between 65 and 80 degrees. And it changes based on the surface roughness and a few other things and the material types. The one in the middle there is what we call internal reflection. And so we're taking advantage. There's that V shape is actually representing the material. And we're taking advantage of Snell's law that says there's a place where the light internally reflects. And so there we've put two surfaces and we're able to turn the direction of that light all the way around. And then the green on the right is the actual refraction where the light's bending and when it goes into the surface. And then if it was to go all the way through, it would bend again coming out. So these are kind of some examples of where we see refraction in use. The picture on the left there is an HID luminaire, and that used internal refraction. It used this from that last slide. It used the center where the light actually enters the material, bounces twice on the inside of a refractive prism to turn it around and send it back down. And the next one over to the right is a wall pack. And those are refractive prisms that primarily, rather than using that total internal refraction, they're grabbing light and just moving it down and also usually controlling it laterally left to right to give a better distribution along the side of a building. The third slide there shows a snapshot of different fluorescent, generally office type lenses that you would see in troffers or LED troffers today, where there's different prismatic patterns. They could be linear, or they could be pyramids, or there were a number of those that were done. They were all intended to help with the intense, with glare control, along with controlling the light in the room and space. And then the last one up there is a spotlight, obviously, a theatrical light. And that's probably a lens that's similar to that Fresnel that we talked about earlier. The total internal reflection, we talked about that a little bit in that refractor in the high bay, but fiber optic cable actually takes full advantage of that Snell's law where the light cannot get out. This particular picture probably isn't the best because it shows cladding. And the cladding really doesn't play a part in fiber optics. It's really more about the light not being able to leave the surface because we've followed Snell's law, and the light will travel down that fiber until it hits something that makes it be extracted. And the beauty of total internal reflection is that there are very, very, very small losses. And so you can pipe light a long ways like they do in fibers and have the light not diminish in strength so that you can then send signals that way. We see a lot of this going on today in the lighting market, not necessarily in a round fiber, but we see a lot of edge lit panels now where we're lighting one edge of a panel, and then on one surface or the other, we would tend to put some prismatic features that would draw the light out. And because of LEDs being small, we're able to light the edge of a panel and do that efficiently. One of the key parts of refraction, and one of the things that comes into terms a lot with lenses, is what some people call transmission. I like to call transmittance. One of my tutors that taught me a lot about lighting used to tell me that transmissions are in a car, And so when we talk about light, we talk about transmittance. And so there's a lot of different ways that transmitting happens, but they're very similar to reflection. We have, you know, direct or image preserving, which is transparent like window glass. We have diffuse transmittance, which is translucent, and that's kind of the semi-specular thing. You can have different levels of diffusion, which fuzz up an image or make an image impossible to see, but still transmit the light relatively efficiently. And then there are spectral changing transmittances, which we tend to not use in lighting because we want surfaces generally to be lit with white light, full spectrum light, we want to say. But the spectral changing thing can show up sometimes if we have real sharp corners or sharp edges. It'll actually separate the light into those bands of color. And so we have to be very careful when we're doing optical design about changing the spectrum. So the other thing that happens in transmittance is because we can't really make a perfect surface, what happens is the light gets in, or most of the light gets in, the incident light gets in, and a little bit bounces off at that first interface. And then when it goes to the second interface to leave, there's actually a reflected component. And every time it hits the surface, there's a little ball of light that is kind of like, it depends on the surface quality and the material, but it could be semi-specular or it could be diffuse. And some of it gets lost and some of it continues down the path and comes out later. And so transmittance is something we have to be very careful of because it is dependent on that incident angle. And one of the questions that we get a lot is, you know, we'll make a lens out of acrylic and somebody will say, well, what's the transmittance of the lens? Well, the material manufacturer tests transmittance of a smooth-sided polished plaque when they're perpendicular to the surface. So if you took that incident ray and pointed it right perpendicular to the surface in line with that arrow that they're measuring the angle from, that's how transmittance is measured by most material suppliers. Unfortunately, most of the light that hits that surface doesn't hit it at that perfect perpendicular space. And so because of some of these losses and some of these other things, transmittances of materials generally range from, of clear materials, generally range from about 80% on up. Some clear materials that are not good transmitters that wouldn't be used for optics are actually below 80%. But optical materials, they generally, we try to stay above 80% in clear materials for transmittance. Those light rays that are bouncing back and forth that tend to never get out, usually they end up being turned into heat. There's not a lot of heat there, but that is the absorption. And in theory, if you took the incident light and subtracted the transmittance light, whatever's left you would say was absorbed. Oftentimes the math doesn't quite work out perfectly like that because there are some other small losses. But absorption is important to understand that every material does use a little bit of that light up. And so you never get out everything that you put in.
Joel, I'm going to pause you for just a second. We had a question that came up on the previous slide, and Chris is asking if there is a difference between acrylic and polycarbonate.
There is two differences in acrylic and polycarbonate that are well, there's more than two, but for optical purposes, there are really two things that are critical in acrylic in the difference. The index of refraction is different. And so polycarbonate has a slightly higher index, which means that the light bends a little bit more than it does in acrylic when it enters, and it bends a little bit more when it leaves. The other difference between acrylic and polycarbonate from an optical standpoint is acrylics are generally have a higher transmittance. Polycarbonate tends to eat up a little more light. It tends to have a little more absorption than acrylic. There's been a lot of work done in the last, I want to say 10 years around LED grades of polycarbonate to get the transmittance up closer to acrylic, but acrylic is still the better as far as a transmittance overall number.
Great, thank you, Joel. And Chris also says, okay, thank you.
Certainly. One of the not necessarily optical difference, whoa, what happened there? Look out. Sorry, come back up here just a little bit. One of the things about polycarbonate and acrylic that are not necessarily optical when you're doing design work, but certainly come into play is the polycarbonate tends to not do well in outdoor environments because of UV degradation. And so acrylic will hold up outdoors for a very long time without discoloring. Every polymer, if it's heated high enough or put under enough UV light, will eventually turn yellow. But acrylic does much better in UV, especially if you keep the temperature down, than polycarbonate does. And so that's another consideration. Here at ALP, we generally tell people that if they're in a vandal area or they're worried about their luminaire being broken in an outdoor environment, then, you know, if we tell them if it's going to be broken within the first 5 years that you put it up, you should use polycarbonate, because the polycarbonate will take some of that abuse. Acrylic is not very high impact, and acrylic will break. And so that's kind of it's a different reason to make a material selection, but sometimes you're willing to put up with a lower initial transmittance because you need the vandal resistance. And polycarbonate is roughly 10 times more impact or 10 times less impact sensitive than acrylic. So we talked a little about absorption. The last thing I wanted to talk about was diffraction. And diffraction is a little bit more complicated. And I don't know how many people can remember back to a physics class where we did a thin slit of paper and shined a light at it and got stripes on the wall. Some of us might have done that, or some of us might not have, but that's what diffraction is all about. And diffraction comes into play in optics if we have sharp edges, as I talked about earlier, or in a reflector, if we were to have a narrow space. And what can happen with diffraction is you can cause striping or you can cause color. And early on, there were a lot of issues with edge color of LEDs, and diffraction and optics tend to really accentuate that. Fortunately, I think the phosphor placement on LEDs has gotten a lot better, and diffraction isn't as big of an issue, but it is something that when we're doing optical design, we have to pay attention to so that we're not causing either a striped pattern or a color separation issue.
Hey, Joel, I'd like to mention right here at that time too, and that is that there are several LEDs out there right now that have what's called high angle yellow. And it's usually accentuated by a lens that's being in play. But basically what that is you know, let's say you're using a 5000K or a 4000K LED, but it has high angle yellow. That means at the very top of the LED coming out unilaterally is mostly yellow light, but the rest of it is all white light. And so when you stare at the actual fixture, you would swear it's 27 to 3000K, but if you took a chromaticity meter and stood below it, you would register 4000K or 5000K, whatever it was supposed to be. But anyways, just as a note, there still are some very high-powered, good LEDs out there that still have that high-angle yellow. I don't want to say issue because it's really nothing wrong with it. It's just that it's a semantics.
That's correct, and you know they have made great strides in LEDs for being able to overcome some of that, but some of it's just the nature of how the LEDs are constructed. And so you're right, there are still a number that have that high angle yellow, and probably will continue to have for quite some time. That's a little bit hard to discuss, and of course measuring those colors, that would be a different seminar that would be longer than a half an hour. Color measurement and the way we see color is a pretty complicated issue, but yes, dealing with that high angle yellow in lenses is always a challenge. So the last thing I want to talk a little bit about is something that I think is really critical in optical design. It's also very critical in measuring light output. And I was first introduced to what I call the 5 times rule in the photometric lab. We have a photometer here, and it's very important that when you take photometric readings, you stay 5 times, a minimum of 5 times away from the largest luminance size. So for instance, if we were going to do a 24-inch diameter circle, so it's 2 feet and the whole thing is luminous, then we have to be 5 times that away. We have to be 10 feet away to get accurate readings. And the reason for that is I tried to explain the reason for that here, and so I'm going to kind of go through this a little bit and explain what I did here, and hopefully this will help clear that up. But on the left, if we look at the little box here, that's essentially, I'm going to say, an LED chip. And so just in from the edge of that ceramic LED chip is where the luminous area started. And so there's a little ball of light, and I show 5 of those here, but in reality, there's an infinite number of these points on this face of this LED that have this distribution. And in any place, if we took a disc and covered the face of the LED and had a pinhole in it, it wouldn't matter where we put the pinhole, we would get the same distribution. And so those things are all additive. But what that means to optical design is that we're dealing with a source size that goes from this top one, which is the edge of the phosphor in a phosphor coated white LED, to here. This entire luminous surface is glowing with this distribution. And so you can see this circle represents, the diameter of this circle represents that distance for this entire surface. And so there is 1 distance away. And so if I come out here 1 distance away and I tried to put any of these optical surfaces, a reflector or a lens surface, a refractive surface, anything I try to do, I'm dealing with many, 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 many angles of light. And I'm only going to be able to effectively control a very narrow band of those with any given surface at any given point. And so the real trick is to get away from the source size. And if we go, there's 1, 2, 3, it's important that I point out, this looks like, boy, this would be a great place right here to control this light. Unfortunately, we have to remember that I only traced 5 points. And so the gaps we see aren't really there. And so there's many, many angles of light, even still at 3, 4. When we get to 5, we're down to only a couple of colors of rays, and they're the rays that are closest to the center. So now at 5 times away, we have a pretty good chance of controlling a majority of the light with a reflective or a refractive surface, and being able to say that if I put an angle there, all the light that hits that is going to come out in a pretty narrow space. It would be even better if I could get 10 times away. But the industry has kind of settled for photometric purposes that originally it was a 10 times rule, but the industry has kind of decided that 5 times away is more reasonable and close enough. But it's important to understand, if we have a fixture that, let's say, has 140 LEDs on an LED board, and they're in a 4 or a 6-inch square, if we really want to control the light from all of those LEDs, we need to be 4 times 5. We need to be 20 inches away. And that's not realistic, so we make compromises in the middle. But when we do that, what we sacrifice is the ability to control all of the light. We then have to decide what the most important light is at any given position, and then do the optical surfaces for that light that we want to gather, and then make sure that the stray light, or the light that goes off from that optic that we didn't want to control, doesn't have an adverse effect. And it ends up being a lot in LED lighting design. It's more about those adverse effects than it is being able to move the light that we need to. And I think it's important to understand that if you're going to get into the optical control side of the lighting business. And I think that that is what I had today. I don't know if you guys registered any more questions.
The one question, we'll wait for see if any more come in, but on top, to piggyback off of Chris's question, talking about the difference between acrylic and polycarbonate, maybe we should also talk about the pros and cons of silicone and lenses.
We certainly can do that. Silicone is kind of a new material to the lighting industry, and when I say new, I'll say 5 years or less. They were able to come out with optical grades of silicone that were highly transmittive and able to be used. They are still considerably more expensive than acrylic or polycarb, but they offer some very interesting characteristics, and that they have high transmittance. They do not turn yellow over long periods of time. We have a test that we do here. I just recently ended a test, and I had silicone samples in a chamber with a 400 watt HID lamp for 30,000 hours. And they were at an elevated temperature, and they did not change in yellowness index over 30,000 hour period. And for standard polymers like acrylic and polycarb at those temperatures, that's pretty unheard of. And so silicone has that advantage. The other advantage that silicone has is that it will take tremendous heat. So it doesn't turn yellow, and it will take heat. The one thing about silicone that's kind of interesting is it doesn't have a good flame rating, and so it actually will burn. If you're going to put it in a place where it needs to be part of an enclosure or enclose wire endings or junctions on an LED board, you have to be very careful, because it doesn't get a rating that will allow that. It just has an HB rating like acrylic does. So even though it takes real high temperatures, it struggles in the flammability categories for UL. But it is a very interesting material, and it certainly has a play because of its heat resistance. It has a very usable place in LEDs where heat is an issue, or with LEDs.
And Joel, touching on that question relative to LEDs and lensing and temperature, it is the case that if a light source or a heat source is running less than 80 degrees Celsius, it will have an impact that doesn't dramatically affect the yellowing of that material. But if it's above 80 degrees Celsius, that's kind of a catalyst. And so a critical issue would be thermally managing the LEDs properly.
Most definitely. And, early on, that really wasn't too big of a deal, because most LEDs, the recommended operating temperature for the LED was down around 60 or 70 C. And so we didn't see those temperatures. But in some of the newer, especially high power LEDs, a lot of those now have temperature ratings that are up, 90 or 100 C. I've seen some even higher than that. And so now that does become an issue. If you're mounting that to a board and a heat sink, and that heat sink is directly in contact with your lensing material, yes, you have to be very careful. 80 C, anything over 80 C in acrylic will begin to accelerate the effects of UV, and anything over 90 C in polycarbonate. It's important to note that UL has higher RTI ratings for both of those materials than that. But RTI really doesn't have anything to do with the ultraviolet effects and the yellowing. And so we kind of derate their performance for lighting because of the yellowing characteristics at high heat.
Thanks, Joel. Another question, and of course this is much more open-ended, but given the rapid advancement of LED technology, particularly within the past decade, without being able to predict what disruptive technologies may come in, where do you see the industry of lensing going forward within the next 10 years? And you know, relative to like whatever may come up along the way?
Well, I think, and I'm hoping that that we're seeing a little bit of a shift back. You know, I have a little bit of a soapbox about this, and I'll try not to get on my soapbox too much. But I'm very concerned that the LED brought about this idea that lighting was about energy savings. And for a long time, everything we did was we'll put up LEDs to save energy. And I think that we kind of lost the idea that we're lighting spaces so we can see better. And there were a lot of early lighting installations with LEDs that I think were pretty horrible. And if you had to be in that environment for very long, the glare and other things would bother you quite a bit. And I see now a motion back towards lighting quality. And I think when we get back to lighting quality, we talk a little bit more about this lensing, being able to diffuse the light and being able to make the source bigger than it really is, especially if we start approaching that 5 times rule, so that now we can take little points of LED light and make them a glowing surface. And I think that's a really critical thing to get us back to a more visual, comfortable space to be in with these new sources. And we're seeing a lot of movement in that direction, and I'm encouraged by that.
Excellent, Joel. Thank you. Yeah, we're also seeing that certainly not only within the conferences and information put up by the IES, but of course, you know, industry-wide as well.
Okay, Joel, we really appreciate your time today, and thank you for joining us. If anybody has any questions for Joel and you think of them later, please feel free to drop myself or Michael Woznicki a note, and we'll pass it on to Joel and get his response to that. So we thank you for your time today, and at this point in time, we're going to close down the webinar. So enjoy the rest of your day and stay safe out there. Thank you, everyone.
Well, great. Thanks, everyone.